back to the material. So, in the previous class, we discussed oscillating system, an oscillating system which was exposed to a damping force, right? Damping force proportional to the speed of the system. So we solved all possible. We looked at all possible situations: under damping, over damping, critically damped. Right, and then at the end of the previous class, we decided to make system more complicated, and we added a driving force. And driving force is a function of t. So we added just in general any force as a function of time, right? And as a result, our second order differential equation, which describes motion of that system, driven, damped and driven system, that differential equation becomes inhomogeneous, right? So now we had a free term, free from x's. So there are no any x's or x dots or x double dots next to that term. So, and in homogeneous differential equation, we discussed how can we find a general solution of a inhomogeneous differential equation. So first you remove the free term so that you have homogeneous differential equation. Solve that. So that will be a general solution of a homogeneous differential equation. And then grab the whole equation in homogeneous and find any particular solution of that inhomogeneous differential equation. And now you have homogeneous solution of general solution of homogeneous differential equation and a particular solution of inhomogeneous. If you add them up, that will be a general solution of inhomogeneous differential equation, right? So that's what we discussed. And then, so we know the solution of homogeneous equation because that's what we did in the previous class. All right, so we don't have to solve it over again. So now our goal, we need to find again emphasize any particular solution. It doesn't matter. You can make it complicated. You can make it simple, right? You can as long as it satisfies inhomogeneous differential equation. So our goal to find that. And of course, you cannot find a particular solution if you don't know explicit form of your driving force. So let's assume that our driving force varies harmonically with time. And we decided to use, I think, cosine function, right? Yeah. Right. So probably I should have written the title, right? So let me just quickly, sinusoidal driving force. Right. So as a result, we assume, so let's assume that our force has this time dependence. So F naught times cosine omega t. So we've done this at the end of the previous class. And again, I'm emphasizing, right, F small, it's not the force, it's an actual acceleration, because you remember how we introduced this F small? It was F capital, which was a force divided by the mass. So these has units of acceleration, right? So it's actually acceleration. So let me remind this. So F as a function of time equals to F capital divided by m. So this is an acceleration. And of course, F naught is the amplitude of the driving force, and omega is the driving frequency, right? And again, I want to emphasize. So now your system is not isolated. Now it's driven, so it means it is exposed to the influence from the outside world, right? So the energy will be dumped into the system, right? So the energy is damped into the system through this driving force, and energy is taken out of the system through the drag force, damping force, right? So driving force allows us to give energy to the system, damping force takes energy out of the system. So we can basically like channel energy through the system. Okay, so as a result, our differential equation look like this, right? So it's still quick review of the previous. Plus 2 beta x dot plus omega naught squared x equals to f as a function of time. You know what? Let me write immediately our form f naught cosine omega t. Right. And yeah, omega naught is the natural frequency. Let me again write natural frequency. It's a frequency of the system which is not exposed to a damping force. And omega is the driving frequency. Driving frequency. Okay, so then again, I want to remind. So we want to find any particular solution, right? So and in order to see, and again, cosine function is a nice function, but we can make it look even more convenient equation. We can make an equation look even better if we go to a complex world. So we will try to solve it by losing touch with reality, right? And just go to a complex world. So you remember we decided to also, let's introduce this equation, 2 beta y dot plus omega naught squared y equals f naught sine omega t. So then we can multiply this equation by I, right? And add these two equations in order to move to the complex world, right? So as a result, z equals x plus I y, and the equation, of course, will look like z double dot plus 2 beta z dot plus omega naught squared z, and equals to f naught e to the power of I omega t. So that's basically, that's where we finished in the previous class, right? So we introduced this imaginary part, and again, it will make our life in terms of math easier. But then, since these two parts, x and y, basically they never overlap, right? So we can solve it in a complex world, and then at the end we can separate them, getting the actual displacement. That's what x is, right? Okay, so again, we need to find any particular solution. You can search for a particular solution in any form. But in this case, it's obvious, since we have exponential time dependence. It makes sense to search for a particular solution having exactly the same time dependence, because it doesn't matter what you do with an exponential function, it will survive. It will give you some additional factors in front, right? But the function itself, time dependence, will leave, right? As a result, we will be able to cancel it throughout the whole equation, right? So in this case, the choice for the solution is obvious, right? So let's seek for a solution. Okay, particular, let me emphasize. In this form, so z equals some constant c e to the power of I omega t, right? Whereas c is undetermined constant. So basically, the goal now is to find just this constant. So the form of the constant which would satisfy this differential equation. So let's just plug it into our equation. You know what? Let me frame this. Right. Then, of course, I will have to address this from time to time, and yeah, this. Okay. It will be easier to find them. All right, so if we plug it, we will get minus omega squared c. So minus c omega squared e to the power of I omega t. Then plus 2I beta c e to the power of I omega t. Right here. And c omega naught squared e to the power of I omega t. And f naught e to the power of I omega t. Yeah, so of course, we knew, of course, exponential terms. Factors can be removed. And as a result, yeah, we need to find this undetermined constant c. So let's just solve that. For that constant c will be equal f naught divided omega naught minus omega squared, of course. Omega naught squared minus omega squared. Okay, let me put it in a bracket. And plus 2I beta. Plus 2I beta. Okay, let me check if I got, yeah. So that's the constant. So with this constant, this function is a solution, because you can have a gazillion number of particular solutions of this inhomogeneous differential equation. Okay, so at this point you can say, okay, we just need to go back to this, right, and start separating our real and imaginary part. But yeah, you can do it. But so let's transform this constant in a slightly different form, because now we need to prepare this for a separation. And of course, it's better to have it in an exponential form. So let's rewrite this complex number, okay, complex constant, not number, complex constant, in an exponential form. So, write it in this form. So some constant a times e to the power of minus I delta. Again, any complex number, you can write it in this form. You remember? From your calculus. Right, and of course, a and delta are going to be real numbers, real constants. Okay, so I'm thinking, yeah, probably I can continue over here. So, so let's massage it. So first of all, imaginary part in the denominator. No, it's the worst possible situation. Let's get rid of this imaginary part from the denominator. So how can we do it? You know, we just need to multiply upstairs numerator and denominator by a complex conjugate of this. All right, so as a result, I can write so f naught. All right, so it will be a complex conjugate. All right, omega naught squared minus omega squared minus 2I beta, and divided by, so this times complex conjugate, it will be square of this plus square of that. Right. So it will be omega naught squared minus omega squared plus, yeah, minus will be from the complex conjugate plus another minus from here, so it will be 4 beta squared. Right? So what's next? So next, this constant is fine.
The omegas are squared.
Squared? Yeah. Damn it, every semester, right, at this point, I miss this square. It's not the first time.
Every time.
All right. Okay, so now, yeah, this constant is fine, right? So we don't have to do anything with this. So we just need to write this in a exponential form, right? So what can we do? How can we do this? Okay, let me draw first this. Okay, so it will be x and y. So real part horizontal, y is vertical, right? So this complex number will be in the fourth quarter. Right. So it will be, okay, let me draw it here. So vector representing that complex number, right? So this will be minus 2 beta. This is omega naught squared minus omega squared, right? So in the fourth quarter. And you remember that we can write any complex number z as absolute value of z times e to the power of I theta. And what is theta? Of course, it's an angle. Okay, let me use this. Measured from the positive x-axis in a counterclockwise direction, right? Conventional angle. But of course, who wants to deal with that angle theta? It's better to work with this angle delta. You see small delta? You know, it looks, I can do it better. It's this delta. And of course, delta, it's theta. Theta is 2 pi minus delta. Right? So if you plug it here, e to the power of I 2 pi is just 1. And as a result, we'll have absolute value of z times e to the power of minus I delta. So now we just need to find the absolute value of z and delta, and we can easily do it from the picture. So now I will continue this c. So c equals I'm thinking which way should I write it? Probably I will just write it. Absolute value I will write here next to this. So f naught divided by omega naught squared minus omega squared squared plus 4 beta squared, and okay, let me put this like this. And so now absolute value of z. So it will be square root of this plus square of that. So it will be square root of omega naught squared minus omega squared squared plus 4 beta squared. Right. So this is z, right, which I use instead of over here, this complex number. And e to the power of minus I delta, right? So delta, of course, I can write also immediately. So it will be arctangent of 2 beta divided by that. So where delta equals to arctangent of 2 beta. Oh, hold it. Why you didn't tell me anything, right? So I missed here omega because I'm looking, something is not correct, and it bugs me, all right? So every time I kind of checking notes and I don't see what's wrong. Okay, over here, when I plug, where's my solution? Here, all right, into the second term. So it will be, of course, differentiate, and after differentiation, omega should be here, right? And I'm writing it, I don't see immediately what is missing, but something is obviously wrong. Okay, omega. All right, omega here. And here should be also omega. All right. And of course, okay, let me here. Okay, I can just erase this omega beta, right? And also here omega squared, right? So here omega. So like a kind of gut feeling something is not completely right. And of course, sooner or later you'll realize that something happened. Right. Okay. So this will be. Let me fix it here as well. So it will be omega squared, and here as well. Okay, let me erase this and add omega squared and e to the power of minus I delta. So delta, okay, now I can write it. So it will be 2 beta omega divided by omega not squared minus omega squared. So let me check. Yeah, so that's the value of delta. Okay, I can frame it. It's an important parameter which we will discuss thoroughly, most likely at the beginning of, no, next class will be the exam, right? And so now also we can introduce amplitude. So let me continue. So this can be partially canceled with that. So will be f naught square root divided by square root of omega naught squared minus omega squared plus 4 beta squared omega squared, right? And e to the power of minus I delta. So it's a times e to the power of minus I delta. So all this construction is just a new constant a. So I will write it here, this constant, next to delta. A equals f naught divided by square root of omega naught squared minus omega squared to the power of 2 for beta squared omega squared. Again, these two constants are very important, so I need to frame them because we're going to analyze both of them separately. Okay, so yes, we managed to write this constant c in a nice exponential form. So now separation of a real part is trivial, right? So now we're going back to this z, right, and use this form of c. So now, okay, let me write back to z. So as a result, z as a function of time, of course, will be a and e to the power of I omega t minus delta. So of course now taking real part, of course, is a piece of cake. X as a function of time will be equal to a times cosine omega t minus delta. So that's the solution, right? Particular solution. Particular solution. You know what? Probably I should add P, emphasizing. So that's particular solution of the inhomogeneous differential equation. So of the equation. Right. Okay, so now we can write general solution. Again, now general solution of the inhomogeneous differential equation, right? So, general solution of the inhomogeneous differential equation so which is x as a function of time. Again, I'm reminding you, so it's a general solution of homogeneous x sub h. It's a general solution of homogeneous differential equation plus a particular solution, right, which we just found, any particular, and we found any. It doesn't matter which form or what structure, as long as it satisfies differential inhomogeneous differential equation. So in the most general case, right, homogeneous solution of the homogeneous differential equation, C1 e to the power of lambda 1t plus C2 e to the power of lambda 2t plus a cosine omega t minus delta. So right now I just use lambda 1 and lambda 2, so it means that it's can be applied for any damping situation, under damping, critical damping, over damping, it doesn't matter. So this can be applied for any of those cases, right? Okay, so before we go, now we have a bunch of constants. We need to discuss them. Which are constants of integration? So right now we have 4 constants, C1, C2, A, and delta. And obviously you see that C1 and C2 are the constants of integration. They depend on your initial conditions. So you set up the system, right? Create some initial conditions, right? You know, push it or displace it, right? And of course, those initial conditions will affect C1 and C2. A and delta has nothing to do with initial conditions. Those are not constants of integrations. Those are just the constants describing the system. Basically like intrinsic parameters or constants of the system. Because what? They depend on what? Delta depends on damping constant, property of the system, right? So we assume that you have an oscillating system which is exposed to some medium, right? Omega, driving frequency, right? Again, if you fix the driving frequency, right? If you don't tune it, right? So okay, it's again property of the system. Natural frequency, again property of the system, and again driving frequency. So it depends only on parameters of the system. So the delta is kind of an intrinsic parameter. Constant. A, the same, depends on the amplitude of the driving force. Again, natural frequency, damping constant, driving frequency, right? So those are basically, if you pick the system, pick the media, those constants are predetermined. Right? But C1 and C2 are constants of integration. Okay, let me emphasize on this. C1 and C2 are constants of integration. Right. So depend on initial conditions. Depend on I dot C. Depend on initial conditions. I dot C. C dot. Right, and A and delta, which way I call them? Not call them. Okay, I just wrote determined by the system's parameters. Right, determined by the system parameters. So then, probably, yeah, I should, since basically this is, not basically, this is general solution, of course, it must be framed, right? So because from this point, we can start looking at some particular cases, particular situations, and before we start looking at some particular cases. This first part, basically this is homogeneous, no, this is general solution of the homogeneous equation, this part, right? It's called the transient solution. Why? Why is it transient? Because since there is a damping force, so of course amplitude goes down. And if you wait long enough, right, maybe a few cycles, maybe a little bit longer, of course the transient solution will disappear. So that's why it is called transient solution. And this solution, this part, this particular solution, is called steady state solution. Right? Okay, let me emphasize on this. So C1 e to the power of lambda 1t plus C2 e to the power of lambda 2t are called the transient solution. I should have named them immediately after introduce so that I can use this space, but I fill the space already with writing, so I have to write it this way. And a cosine omega t minus delta are steady state solution. Steady state solution. Right. So again, if you wait long enough, transient solution will disappear, and the steady state solution will live forever and ever, happily ever after. All right, so let me check if I mentioned everything which I was planning. Yeah, and of course, if you look at the steady state solution, right, so it oscillates with what frequency? Frequency of the driving force. So driving force is powerful and it forces the system oscillates with its own frequency. But of course, the system lags behind because of this constant delta, so the system doesn't respond instantaneously, immediately. First it thinks before responding, right? But of course, in which case, sort of what's the reason of this, of the fact that a system lags behind? Again, what is this? It's an X, it's a response of the system, it's a displacement of the system from the equilibrium, right? So why does it lag behind? It's a consequence of the fact that it's exposed to a medium, so because there is a damping force, so it has to get through molecules of air, of water, or oil, whatever, right? And so that's the reason for the fact that it lags behind. In which case it doesn't lag behind, it's when, of course, delta equals to 0. When does delta equal to 0? When beta equals to 0. Right? If beta equals to 0, then delta constant is 0, and in that case, the system will respond instantaneously, immediately, right? So if the force at the maximum is at the maximum, right, then the displacement of the system will be at the maximum, right? Force goes to minimum, right? The system goes through the equilibrium, right? But if we have a damping force, if a damping constant is not 0, then of course the system every time will be slightly behind of the driving force, which is of course makes sense. All right, okay, so now let's apply this for an under-damping case. Basically now we slowly, after this point, we basically started preparing sort of like a platform to move and discuss resonance, right? So of course that you can observe if you have a light damping, right? Very light damping. So now let's write this solution for under damping case as a preparation, basically, to discuss resonance. Okay, I'm thinking, should I? Okay, probably I will still write over here. No, since I will have to draw the picture. I will need more space, so I'll move here. So at this point, I will just need these two constants, so I can erase it all. Right. In case of underdamping, so in case of underdamping, of course we can write solution in. Probably first let me write. So of course, what does it mean underdamping? Beta is less than natural frequency of the system, right? So the general solution, of course, can be rewritten in a slightly different form. So let's use phase-shifted cosine solution. You remember that A cosine omega t minus delta. But since we already have A and delta over here, these constants, so let's use constants A sub tr, which stands for transient, basically because now I'm rewriting this part of the solution for the case of underdamping. Steady state solution doesn't care. Underdamping, critical damping, or overdamping, it just lives its own life, right? Happy life, actually. Forcing the system to oscillate with its own frequency, right? Right, so A, TR, again, TR stands for transient, right? So let me emphasize. So this is stands for transient. Then, of course, there will be damping, right, factor e to the power of minus beta t, right? So the damping constant, of course, in underdamping case, that damping constant is also decay parameter. So it will be e to the power of minus beta t and cosine of omega 1, right? It's a frequency of the system in case of damping, omega 1 t minus delta, again, tr, again, stands for transient. Right? Again, to sort of distinguish them from these constants. And plus a cosine omega t minus delta. So that is a special case of this solution, right? Again, this can be applied for any situation, and this is for underdamped system. So now I just want to plot, right, to again emphasize on one case, and probably again I will emphasize on this, that this is the transient solution, and of course this is a steady state. Basically that's what I wanted to do over there, but I filled the space with writing. As a result, I didn't have space. Steady state solution. Okay, so now if you wait long enough, so what do I mean by long? Beta in this case, in general, it's just a damping constant. But also at the same time, it's a decay parameter, basically a parameter which describes how fast system dies out, right? And we can also introduce sort of like a decay time. It's a 1 over beta, right? 1 over beta decay time. At that moment of time, amplitude goes down to 37% of its maximum value, right? So wait long, we can say, so when t is much larger than 1 over beta, which we can call a decay time. So it's basically a moment of time when amplitude gets reduced by a factor of E 2.7, right? So which is 37% of its maximum value, of maximum value of the amplitude. Right, so of course, if you wait long enough, of course, what happens with this term? It becomes very small. We can damp it, and we will have only steady state solution. Right, so that's why most of the time, right, most of the system oscillates for a long time, especially driven system, right, like a clock or radio. There are tons of oscillating systems like this, right, which oscillates over a long period of time. Then, of course, it doesn't make sense even to discuss this. So, major interest is in the steady state solution, right? So, so the transient solution, the transient solution will disappear, right? And only steady state solution leave, right? So which way? So the steady state solution is of the major interest, Okay, so I remember I promised to plot something. So let's plot. I just want to sort of juxtapose the time dependence of the driving force and the time dependence of the system's response. Right. So let me plot. Let's say this is F force versus time. Right. And in our case, the force is a cosine function. I erased that, but it was here. So let me plot cosine function. So let's say it's something like this. Right, so this is F naught. Okay, so now let me plot the response of the system, again, which is X, right, versus, you know what, probably I should have made more cycles. Okay, I still have space. Let me increase this x-axis. So time, and this will go into the next cycle. So the response of the system. Let me overlap this. So this will be here. This is here. Right. So the steady state solution shifted, of course, in phase by delta. But of course, since we're plotting time, so the response of the system lags behind by what? Delta over omega. Right. So you see when t equals delta over omega, so cosine will be 0. And so it lags behind by delta over omega. So if force reaches maximum at this point, right, at t equals 0, the response of the system will reach maximum. Okay, maybe I will use again blue at this point. So, and this distance is delta over omega. Again, distance in time interval. So delta over omega. So at this point, the system will reach maximum. So lags behind. Force reaches here. System response reaches maximum only a short period of time later. Okay, maybe not so short, but later. Then, of course, it will crosses 0, again, lagging behind. So something like this. Basically, right now, I'm plotting only a steady state part of the solution, right? And then on top of that, I will show the transient solution. So then, of course, maximum will be shifted over here somewhere. So, okay. Then again, it crosses 0, shift. With a shift, then again reaches maximum, being shifted, and again 0. Okay, it's distorted, but so that's the transient solution. And okay, not transient, steady state solution. It's a steady state solution, right? So that's again steady state part. And now what about transient, right? Transient, yeah, it will be have amplitude A, which goes down with time, and it oscillates. Basically, with different frequency, right? So what is going to do here? So basically, on top of this transient solution, we're going to have maybe over a couple of cycles, we can observe our transient solution, right? And then, of course, it depends on how strong damping is. And then sooner or later, it will disappear. All these ripples on top of the transient solution will be washed out. And as a result, at the end, if we again wait long enough, where is my here? Right. So sooner or later, we will have only a steady state solution. And another thing which makes me feel sad about this system, let's say you build the system, right, and you maybe created some initial conditions, right, for your system. You expose your system to your initial conditions, right, and where are the results of your initial conditions? Over here in this delta TR and ATR. And after maybe a few cycles, all your efforts in setting up initial conditions will just disappear. The systems will completely ignore it, not ignore it, but sooner or later it will forget about them completely, right? So all your initial conditions, all your efforts over here in these ripples around the steady state solution. All right, so in this case, there's no point of setting up initial conditions, right? Because the driving system will dump them all. Okay, so okay, maybe I will write. So the system lags behind. So the system, lags behind by t equals delta over omega, right? All the time. And of course, yeah, as I said, if there is no damping, if beta equals 0, then delta equals 0, and then of course the system follow the driving force in no time, right? So force is at maximum, the response of the system will be at maximum. The force will go to 0, the system will go to 0. So it will be, all right, in phase. Okay, so now, good, all right, and you know what? I will keep those constants, and I will probably start erasing this. Now, we have to carefully, basically we know the response of the system. So we solved the problem. What else do we want? So now we just need to look at these two constants, analyze them carefully to see maybe something interesting we can observe, right? So first we will look at A. And probably next class, okay, in a class, because next class will be the exam, right? So we will look at the phase shift, right? Okay, but so for now, let's look at this constant. And I feel like probably I need to, okay, let's first discuss and then I will write the title. So let's look at this. First of all, yeah, this is the amplitude. It depends on the amplitude of the driving force, natural frequency, driving frequency, damping, and driving frequency. Let's look at the system in this way. Amplitude of the driving force is given. The system is given, so whatever oscillating object is. So as a result, and the restoring force is given. So as a result, omega naught is fixed, given. So we're not changing this, right? Beta also is fixed right now. So we exposed our system in a certain medium, right? So the damping constant is fixed. So everything is fixed, but driving frequency. Basically, let's say you have a driving force, and which is, I know, powered with some function generator, and you can control the frequency of that, right? So there is a knob, and you can increase omega, you can decrease omega, right? So you can explore behavior of the system if you change a driving frequency, right? Okay, so basically omega, now is like a variable for us. The rest is fixed, right? If we imagine this situation, right? So then, obviously, amplitude depends on omega, right? And in this term, there is a difference between natural frequency and the driving frequency, right? And if we move omega, because again, it's a variable, we can control that. If we move omega closer to the natural frequency, this term becomes smaller and smaller and smaller. As a result, the whole denominator becomes smaller, right? Becomes smaller, and as a result, amplitude becomes larger. Or if we move omega farther away from the omega naught, then of course this term becomes larger, the whole denominator becomes larger, right? And as a result, amplitude gets smaller. So by tuning the frequency of the driving force, by tuning the frequency of the driving force, we can control the amplitude. And of course, if we can control that amplitude, of course, the natural question, where are the maximum, right? Or maybe there are several, or maybe one, or what about minimum, right? So of course, it triggers immediately the desire to explore that amplitude. Searches maybe for the maximum, right? Basically, maximum amplitude is basically maximum response of the system. You cannot get any better than this, right? So basically, at that moment when you have the maximum response of the system, so the system oscillates like crazy, right? To the maximum craziness of the system. At that moment, basically, you create the most effective or efficient channel of damping energy into the system. Again, so now our system is not isolated. You remember I told you. So now since we have a driving force, through the driving force we can give energy into the system. Through the damping force we can drain energy out of the system, as I told you, right? So we have we're channeling energy through the system, right? But for now we assume that damping force is fixed, the system is fixed, so we're just playing with this channel of damping more and more energy, or maybe less energy into the system, right? So during the resonance, when the response of the system is the maximum, we create the most effective channel of damping energy into the system. As a result, system is very happy and have a party in the full swing, right? Okay, so now let's see when can that happen. Basically, let's search for the resonance, right? For the resonance conditions and so on. All right, so you know what I'm going to do? I will, because I want to feel free to erase whenever I need something. Let me rewrite this constant over here somewhere, all right? Because now I don't think that I need this. And then I will start analyzing that function on that side. Or maybe I will just, no, I will write here in the corner. Okay, this constant I will need next class. So I can erase this. And this definitely can also be erased. And again, you remember, we are in an underdamping case, because resonance makes sense to discuss only in underdamping case when you don't have any oscillations, so there is no any point of even looking at the overdamping or critically damped case, right? Because there are no even oscillations, right? And again, most of the time, it's even not just underdamping case, it's a light damping, when beta is much, much smaller than omega naught, right? But first, let's just look at underdamping, and then we will, of course, switch to light damping. Okay, so now let me write, so resonance. And again, I will emphasize it's underdamping case. Okay, I will just write emphasize. So it's a under damping. Right. So again, critical damping, over damping. There's no point of going over there. All right, again, so we have, I will just rewrite. So we wait long enough so that transient solution disappears. No one cares most of the time about. So we wait long. Again, beta, not beta, t is much larger than 1 over beta. So as a result, the solution is just a steady state solution. And with that amplitude, on purpose, I left it over there. Right, so A cosine omega t minus delta. So that's the steady state solution now. And this is our amplitude. Okay, so I managed to recycle. I thought about just rewriting, but I managed to reuse it. All right, and so now, and you know what? Let's analyze not a, but a squared, because whenever I see these square roots, right, they make me feel nervous, right? So, because again, dealing with those square roots, not very pleasant. So let's just look at the square of amplitude. Again, we're not changing anything, right? So again, still the resonance will be at the same point, the same conditions, right? Let's just try to make our life a little bit easier, right? So let's look at a squared. So this is squared, and of course, this square root will disappear. Right. You can rewrite, of course, I can just recycle. Recycle is good, right? So that's what I'm doing. Right. So we just, again, we treat the system with this way. All these parameters constant except for omega. Omega is our variable. You remember I told you we have a function generator, and we can change the frequency of the, we can tune the frequency of the driving force. You can go up, down, right? So you can scan the whole frequency range, right, available to you. Right. Okay. So let me say so everything. Everything is fixed. By everything, I mean F naught, omega naught, beta, right? And we just tune omega. And we tune omega. So basically, so omega is a variable. And so we basically want to explore the response of the system by changing the frequency of the driving force. Right? Okay, so basically this is a function of omega. Finding the maximum of function, what can be easier than that? Of course, it can be tedious, but strategically it's quite straightforward, right? So a squared is the function of omega, right? So we need to find where points where this is maximum. So we need to find max. We need to find right. But you know what? Since we have constant divided by whatever we have in the denominator downstairs, it's easier to switch from finding maximum of this function. Let's find the minimum of the denominator, right? Or let me call it z minimum, right? So what do I mean by z? It's that denominator, omega naught squared minus omega squared squared plus 4 beta squared omega squared. It's ugly squared. Right. So instead of finding maximum of that function, let's just find minimum of the denominator, because upstairs it's just a constant f naught, right? Makes sense, makes our life a little bit easier, right? And again, it's a function of omega. Let me again emphasize. So it's a z function of omega. I should have emphasized on that. Right. So first stationary point, let's find stationary point. So dz over d omega, right? So if you differentiate this, you will get what? 2 omega naught squared minus omega squared plus 8 beta squared omega. Right. No, nope, not enough. Times 2 omega. I'm looking, something is not right. Times 2 omega, and then plus 8 beta squared omega, right?
Would it be times negative 2 omega? Because there's the negative omega squared.
Yeah. Am I? Yeah, absolutely. Negative 2 omega. So now let's factor out, I think, 4 omega. Yeah, 4 omega. Let's factor out 4 omega. And what will be inside? 2 beta squared, that, and then minus from here. So it will be minus omega naught squared plus omega squared. If I'm not making, no, something is not good. No, it's good. No, it's good. Everything is right. Now I started doubting myself more than usual. Right, so, and it must be equal to 0, right, in a search for a stationary point. So, as a result, we have two solutions. Omega 1 equals to 0. But what about this solution, right? Again, you remember, okay, it's just the first solution for the driving frequency. It's not that omega 1 which we had when we discussed the damping cases, right? You remember that? It's completely just by accident we have the same notation. This is just a first solution of this differential equation. And again, it's a frequency of the driving force. If the frequency of the driving force is 0, that's what? That's just a constant force, right? It's nothing is interesting over there. Example of this case, it's sort of, let's say you have a spring and mass, position vertically, right? And you have a constant force acting on the mass. It's a driven system, driven with the driving force which doesn't have time dependence. So what happens in that case? It's just the position of equilibrium gets moved, right? So the equilibrium will be slightly lower, right? And then the system will oscillate in exactly the same way. So this is not much of a, nothing interesting. Nothing interesting. It just displays an equilibrium of a driving system, right? So it's a constant force. So maybe I will write like F equals mg, for example, right? So we're not going to discuss that. And of course, the second solution, omega 2, will be equal square root. So we're solving for this, so it will be omega naught squared minus 2 beta squared. Omega naught squared minus 2 beta squared. And of course, that will be our resonant frequency. So right now, of course, it's just a candidate, right? Because we're still we don't know what will be at the end. But of course, we know that will be, at this point, the response of the system amplitude will be maximum. So this will be the resonant frequency. Okay, so although we haven't shown it yet, but I will frame it. And of course, I will label it resonant frequency. So at this frequency, of course, the response of the system will be the maximum possible, right? Again, God created nature this way, so if you use different frequency, of course, the system will respond. Response of the system will be worse. Okay, but anyway, so let's look at the second derivative in order to convince ourselves that we're going to get, now in this case, you remember we're exploring z for minimum, right? So the response of the will be positive, right? So let's look at the second derivative. Z over so it will be, this time I will skip it. I mean, skip calculations. It's just a couple of lines of doing over stuff like here, right? And it's kind of tedious usually, and so easy to make some silly mistakes. So at some point I started skipping those calculations, right? All right, so this is what we have square. Let me just check my notes. Not 8, it's not 2, 8, sorry. 8 omega 2 squared, right? So second derivative positive, it means it's a minimum, right? So z at, and again, it's at omega 2, right? So of course we are evaluating the second derivative at this point, right? So positive, so z is minimum, and of course, as a result, a at omega 2 is maximum, right? So yeah, good. So this point is going to give us minimum of this function, and of course, as a result, maximum of that function, right? So yeah, this is the point which we needed. And now, so what's next? So what's the value of the response? Let's find the amplitude at omega 2, right? So I think, yeah, let's first find the square of the amplitude, right? So a squared. So now a squared at when omega equals to omega 2. So let's find the value of amplitude. You know what? We are getting closer to the end of the class, and I can use this part because it's difficult to write over there. So now I don't have to think about space. So if we plug into a squared at omega 2, it will be f naught squared and divided by all that omega naught squared minus omega squared, so it will be minus omega naught squared and plus 2 beta squared, plus 2 beta squared. So that's must be squared and plus 4 beta squared times omega squared, so it will be just this. Omega naught squared minus 2 beta squared. Whew. Right. So this goes, and it will be 4 beta squared. So let's factor. Okay, let me first write numerator f naught squared divided by 4 beta squared. This will be omega naught minus 2 beta squared, and here plus, right? So it will be another beta squared, it looks like. Right? Let me check. Yeah, plus beta squared. So as a result, it will be omega naught squared minus beta squared, and that's what I have in my notes. Yeah, so it's good, it's good.
Isn't beta raised to the 4th outside of the parentheses there? Since you're squaring beta squared?
No, yes, this will be 4 times beta to the power of 2, but I'm taking 4 beta squared outside, so beta squared will be left, and this is beta squared. The one which you mentioned, it's over here.
Okay.
So this, okay, you see I flipped the terms. So first I factor out 4 beta squared. So, and first I wrote these 2 terms. There, here they are. Right, this.
Yeah,
and then only that, right? So beta squared,
yeah, okay.
If you multiply, you will get this 4 beta to the power of 4, right? I'm
Cool.
also
Thank
very
you.
often, especially when you work on the whiteboard, you can easily miss all this. So sometimes I try to skip some of this, just write from my notes, right? 4 beta squared and omega naught squared minus beta to the power of 2. So that's the amplitude at the resonant amplitude of the system at the resonance, right? And so, yeah, of course, you can take a square root. Right now, it's a square of the amplitude. But again, most of the time, systems which we examine, explore on the resonance, right, trying to avoid it or trying to achieve it, right, whatever applications, right, you deal with systems which exposed to a very light damping situation, very light damping. So let me write. Probably I should frame this first, right, because it's important, right? And now for a light damping, right? So in this case, beta is much smaller than omega naught, light damping. So as a result, beta over here is smaller. We can ignore it, right? So we'll have f naught. So a, I think I can write, and you know what? Probably should here add subscript max. And now I will add here as well. So a max equals, now I will take a square root. Okay, I forgot here square root. Right, so it will be f naught divided by 2 beta omega naught. 2 beta omega naught. Again, for the light damping, very special case. So, and of course, now if beta is too small, of course you can get, okay, the system can be endangered, right? So amplitude can be so large that construction might not survive, right? And of course, you know what, probably I should mention also as well, since we went to this extreme for very light damping, what will be with the resonant frequency? This is very small, can be neglected relative to this, right? So it will be omega 2 equals to the natural frequency. So I will emphasize. So omega 2 will be approximately equal to the natural frequency. But again, it's only for a damping case. I mean light damping case. Right? So now if beta goes to 0, very small, then of course amplitude goes to infinity and system can be damaged. Whoa, why my cell phone is not ringing? Okay, now I need to check again. So the system can be damaged. Right. Okay, so we will take from here next class. Again, next class will be the exam, right? We will discuss, we will plot this amplitude, right? So look at different betas, right? And then some examples. And then we will discuss that constant delta, right, which describe the phase shift of the system, right? And after that, after discussing that phase shift, we can finish this chapter. So most likely we will do it, not most likely, we will do it on Thursday, right? It will take us maybe, I don't know, 20 minutes, okay, maybe slightly more. And after that, we will start preparing ourselves for the Lagrangian formalism. We will start discussing calculus of variations, maybe 1.5 or maybe maximum 2 classes of preparation, and then calculus. And then Lagrangian formalism. And then we will start discussing Lagrangian.